Yes, we'll talk of electron affinity. Let us define this. Electron affinity. And electron affinity is the energy released. The other one is said ionization energy, the energy required. This one is the energy released. That means when you add an electron to an atom, you release some energy. Yes, you release energy, not you don't require the energy. Is the energy released when an atom in gaseous state gain an electron in the outermost energy level. Good. Is the energy released when an atom in gaseous state gain an electron, the chlorine gains an electron in the outermost energy level. Electron affinity. So instead of ionization energy, we'll be talking of electron affinity. I've said that too much. Now let's see what it is. For chlorine, I'm afraid that, okay, I saw that I already deleted the atoms. Let me draw them again. Fluorine, 2, 7. Chlorine, 2, 8, 7. Two, 8, 7. 2, 7. Those are the atoms. And an electron affinity is the energy released when an atom is in gaseous state gains an electron in the outermost energy level. When they gain an electron, when you drew the ion, we indicated that an electron is being gained. So you want to gain this electron. For it to be gained, there's some energy that will be released. Some energy will be released. And if it is being released, no, our concern here, how is it down the group between fluorine and chlorine? Is it increasing or decreasing? What energy will be required? So we start reasoning and we see that fluorine has a smaller atom. Yes, fluorine has a smaller atom. So the nuclear charge applies to everything from metals all the way to gases, all the way to noble gases. Yes, they got nuclear charge too, because it is the attraction between protons and electrons in an atom. So we are talking of the small atom fluorine. It is smaller as compared to chlorine, and therefore it holds its electrons firmly. Fluorine holds its electrons firmly as compared to chlorine. Yes, that one we know, and you have seen that severally. Because this atom is big, the electrons are not so firmly held because it is big. It is baggy. It is big. The electrons are not so firmly held. Fluorine, they are firmly held. And therefore, when there's an electron here somewhere, here somewhere, it has to be gained by these two. Let us say it is of the same distance. It is the same distance from both of the atoms. Which atom will attract it? Which atom will attract it? Will it be attracted more to fluorine or to chlorine? Remember, this one is big, and the nuclear attraction is not so much. It is there, but not as much as in fluorine, and therefore, since this one is attracting its electron firmly, and there's this electron from the outside that want to be gained, it will be easily gained by fluorine as compared to chlorine. It will be easily gained here. And therefore, this one, because of the nuclear attraction, it gains easily. Good. It gains easily because of the nuclear attraction. So the question comes again. Where is, we are talking about the electron affinity. Where will more energy be used? We want it to gain. For this one to gain, it gains so easily because it is being pulled. We have a high nuclear attraction. It gains so easily. But for this one, you have to force it in. Okay, chlorine is very reactive, by the way, but it is because I'm comparing. That is why I have to say that chlorine. This one will have to. It will require some more. Oh, sorry, more energy will be released. We are talking of energy being released. Chlorine will release more energy for it to gain this. Yes, more energy will be released. But for this one, it will be a bit easy. It will be a bit easy because gaining it is easy. And therefore, we want to see if we are making the right conclusions. Let us first talk of the trend. We have said that this one, more energy will be released. This one, because of the attraction, little energy will be released. More little. And therefore, I deleted the table. Is it the table? Yes, the periodic table. But if it was there, I'll still use our arrow. We said we are discussing them downwards. Yes, downwards. And I've just said this one is more energy. And the conclusion will be we are talking about electron affinity. The energy is increasing down the group. The energy is increasing down the group. Increasing. The electron affinity is increasing down the group. For sure, this one you have not to check if you have reasoned in the right way. And here I write the electron affinity for both chlorine and fluorine. Electron affinity. Does it? We have just seen that it increases down the group. This one pulls easily. It can gain an electron easily, so it won't release a lot of energy because it is easy. This one is a bit. It requires. This is hard because of nuclear attraction. It does not gain that easily. Therefore, a lot of energy will be released when it gains. Let us see if that is the right discussion. We are talking of halogens, electron affinity. Are they indicating it? Yes, it is indicated. And they say electron affinity for fluorine. Oh, sorry. I was supposed to start with fluorine here. Electron affinity for fluorine. I write as it is, then we see if the discussion is right. The electron affinity for fluorine is negative 322 kilojoules per mole. I won't write the formulas. The calculation, the symbols. Electron affinity for fluorine is negative 322 kilojoule per mole. That of chlorine is negative 349. Those are the right values. Maybe I can write for, no, it is not so regular. The other one, bromine, negative 325. Negative 325. Ah, no, not so regular. Let us compare just the first two. Now because this one, there's a disparity, let's compare this and this so that you can see how the electron affinity is the trend in it. So you have negative 322 and negative 349. And the question is, how is the trend? You talked about the energy being released. So this topic now, it involves some enthalpy changes. Yes, that is a Form 4 topic, because now we have to determine is the reaction exothermic, endothermic. I won't say what it is because, okay, and a reaction that involves release of energy to the surrounding. Energy is being released. I think it is exothermic. I think exothermic. It is producing some energy. Exothermic. So we check on that. Some energy is being released. Which one is releasing more energy? Let us assume the negative sign, because the negative sign simply shows that it is exothermic. And when I say exothermic, I am not be quoted. Exothermic. Exothermic. The reaction is exothermic. It is producing energy to the atmosphere, sorry, to the surrounding. Okay, that is not the topic of today. The topic of today, we want to compare fluorine and chlorine, the electron affinity. So we will do better without the negative sign. I know if we interpret mathematically, it will mean something else also different. But now, since we are talking of energy, it is very evident that electron affinity is increasing down the group. We have not interpreted it mathematically. We have interpreted it in terms of the energy being released. Mathematics will mean something else, but which one is releasing more energy? Of course, it is chlorine. Hence our trend here. Thank you. So we have gone to energy levels, atomic, ionic radius and their comparison, electron affinity. Let us talk of melting and boiling points. And when we talk of melting and boiling points, when it comes to this, and remember we are in nonmetals, the first thing to say is that these are molecular substances. Yes, they are molecular substances, and they generally have low melting and boiling points. Generally low. First, something else to say is that these are gases. They are gases at room temperature. Yes, chlorine is a gas, fluorine is a gas. They generally have low melting and boiling points because they are molecular substances. And molecular substances, they also have weak van der Waals forces, and that is why they have low melting and boiling points. We want to compare which one has a bigger melting and boiling point. And since these halogens, when you check on tables, just as I said here in electron affinity, they are showing disparity. You look for this one, they had a perfect trend. If it is increasing, it is increasing downwards all through, increase. But for this, sometimes the trend is not so regular. So, but now in that case, we will only be comparing for fluorine and chlorine and leave alone bromine, iodine, and the rest. But in any way, when you compare the two, it means that even if they are sometimes regular, maybe you can check on the common trend, or maybe you reason out to say from your reasoning, and because the trend might not be so regular, you can say or you can derive the trend. Okay, we're talking of melting and boiling points of fluorine and of chlorine. The same definition or the same word knowledge comes to our mind. And we say that fluorine is a small atom, chlorine is a big atom. The nuclear charge here is more. The nuclear charge here is more, a higher nuclear charge. And what does that mean? If it has a high nuclear charge, there's something I wrote here. For metals, the smaller the atom, the stronger the bond. I believe it is visible. For metals, the smaller the atom, the stronger the bond. And that one comes from the metallic bond. We said if the atoms are very small, it means a stronger bond. Like for lithium, 2-1. If the atoms are very small, the bond is very strong, because that was the first factor that was affecting the strength of a metallic bond, the size of the atom. If the atom is very small, it means a strong metallic bond. That is how the first statement is saying. For metals, the smaller the atom, the stronger the bond. Now we have vice versa for nonmetals. Vice versa for nonmetals. It does not apply here. So fluorine having a small atom does not translate to a strong bond. No. In this one, you said vice versa. So it means for nonmetals, that is the vice versa of a statement. For nonmetals, the smaller, which parts now should we change? For nonmetals, the smaller the atom, the weaker the bond. That is the vice versa of the statement. For nonmetals, the smaller the atom, the weaker the bond. Or for nonmetals, the smaller the bigger the atom, the stronger the bond. Okay, you can write that. You can choose which statement is easy to have it in your head. Let me write it here. No, I write only the part for nonmetals, or maybe for these atoms. Yes, for nonmetals, a bigger size atom, the bigger the size of the atom, it leads to a stronger covalent bond. It leads to a stronger covalent bond. So the strength of a covalent bond will be determined by the size of the atom. The strength of a covalent bond will be determined by the size of the atom. A big atom will mean a stronger covalent bond. Now you have that in our head, and you can continue and compare the melting and boiling point of these two. The bigger atom, this one, will form a stronger covalent bond than fluorine. This one will form a stronger covalent bond than fluorine. What does it mean? If the bond is stronger, it means a lot of heat will be required for it to melt or boil. It requires a lot of heat because it has a stronger bond. From this statement, a bigger size atom leads to a stronger covalent bond. Therefore, chlorine has, so I'll get the values from the tables from my reference. So, but now I'll have fluorine and chlorine. We'll use the melting point. I hope it will be a bit regular. If it fails, we use our boiling point. But you have said that a bigger size atoms form a stronger covalent bond. That is one. And when you hear anywhere the metallic bond strong, the covalent bond strong, if the bond is strong, it means that a lot of energy will be required to break the bond. A lot of energy is required to break the bond, and this a lot of energy will mean higher boiling and melting points. Let me indicate the melting points of these two elements so that we can see what statement is right, because what you are suggesting is that it is increasing down the group. It is increasing down the group. This one has a higher melting point than fluorine. Let me write it. The melting point of fluorine, they suggest it is negative 238, very low, and chlorine is negative 101. And when it comes to melting point, we'll have to interpret this mathematically. Yes, let us interpret it mathematically. The melting point of fluorine is negative 238. The melting point of chlorine is negative 101. Now from mathematics and from my mathematics, let us see which one is higher. Which one is higher between the two? Which one is higher? Is it fluorine or is it chlorine? Which one is higher? And the higher one is this one. This one is higher. It is closer to 0 than this one. If you draw the number line and we have 0 here, we will have our negative 100 over here, and our negative 238 will be further away. So this one is higher than this one, because as we go towards 0, then further, it means that is an increase. The one that is higher is negative 101, and therefore the boiling points and melting points of halogens increase down the group, as we have just said. They increase down the group. Increase down the group. This statement seems to be very helpful, even with the vice versa, because the vice versa is simply mean the opposite. That for metals, the smaller the atom, the stronger the bond. But for non-metals, the bigger the atom, the stronger the bond. It is the opposite. I want to repeat that. Maybe you can take note of it. Now, let me just read the boiling points and see if they are following the same trend. The trend for the boiling points of fluorine. Fluorine has a melting point. Oh, that was melting point. Fluorine has a boiling point of negative 188 and a melting point, and chlorine has a melting point of negative 35. So the same case holds, that negative 35 is higher than negative 188. Done with the melting and the boiling point. Let us go to electric conductivity. Electric conductivity. As I have just said, that these substances or these elements are molecular substances. They are molecular substances. They are molecular substances. We say that metals conduct electricity. These ones are good conductors of electricity, simply because they have delocalized electrons. They have delocalized electrons. But for these substances, chlorine and fluorine, they are molecular substances, and they have no delocalized electrons. They have no delocalized electrons, so they cannot conduct electricity. So the conclusion is, halogens are poor conductors of electricity. Full stop. Reactivity. And when I talk of reactivity, I'll come back to this case. The structure of the atom, very important. Drawing these two. Now we want to say which one is more reactive than the other. Yes, we have talked of the covalent bond of this one being stronger than this one, but now in reactivity, I believe we still have now to follow the old formula and say that this atom is very small. This atom is small. Let us reason out to the end. This atom is small. Fluorine 27. This atom is bigger. Chlorine 287. Both of these atoms, to react, they will have to gain an electron. For them to react, they will have to gain an electron. One electron. Which one will gain faster than the other one? Okay, let us reason out. Fluorine has 9 protons, 9 electrons. Fluorine has 9 protons, 9 protons, 9 electrons. This one. And therefore, the nuclear attraction is higher in fluorine, simply because of a higher nuclear charge. In fluorine, we have a higher nuclear charge that translates to electrons being pulled closer to it easily. But for chlorine, it is a big atom. 17 protons, 17 electrons. It is not pulling them that much. There's a nuclear charge, but not as much as in fluorine. So, and that is when we had said, assuming we have an electron outside here, this one has a high nuclear attraction as compared to this. Where will this electron move to? Will it go to fluorine or to chlorine? This one has a high nuclear attraction. It is pulling its electron so much towards the center. But this one, there's no much nuclear attraction. And therefore, this electron will be pulled to fluorine. And hence our conclusion that fluorine is more reactive. Fluorine is more reactive. Is more reactive. Yes, fluorine is more reactive simply because it has a higher nuclear charge because it has a higher nuclear charge that makes it easy for it to gain an electron. Yes, it is easy for fluorine to gain an electron because it has a high nuclear charge. It is pulling its electron so much to the center that when an electron is introduced here, maybe by an element like sodium, it can easily gain it as compared to chlorine. So fluorine is more reactive. And there we can conclude and say, using in the periodic table, using an arrow downwards, what can we say? That reactivity is, this one is more reactive, that is in our mind. Therefore, reactivity is decreasing down the group. Decrease